Bir sonraki sunumumuz için mobil ekibimizden Ali'yi Swift ile modern eş zamanlı programlama konusunu anlatmak üzere davet ediyorum. Hoş geldin Ali.
Hoş buldum. Güzel, teşekkürler.
Rica ederim. Sunumunu paylaşıyorum. Kolay gelsin.
Teşekkürler. In today's talk, we are going to talk about modern Swift concurrency. So let's take a look. First, let's see what's concurrency at the first place. In one way or another, you came across choosing between performing a specific task synchronously or asynchronously. Both they can come in many different shapes and forms. The abstraction that will prove to be best fit might vary quite a lot from one use case to another. Let's say that you are building a social networking app and that you offer our users the option to attach both photos and videos when publishing a post. Currently, when the user hits publish button, we call the following function, which uploads all the attached media and also uploads the data for the post itself, like this. First, we try to upload a photo, then we try to upload the video, then we try to publish the post. While this code is very simple, there's a few problems with it. First, there's no way for us to get notified whenever the publishing of a post was finished. We also don't do any kind of error handling, which means that if a photo or a video fails to upload, we'll just continue uploading the data, the post data anyway, which is not ideal. There's quite a few numbers of ways that we could go about solving this problem. The most common way for us is a ClosureBased approach. First, we define a completion handler closure. Then we try to upload the image as we did before. The image URL back, the response. After we upload the video. Eventually, we ended up with very deeply nested closure that is hard to read and hard to track down. Luckily, it turns out all we have to do to gain the control is deeper into the stack and use the framework that many of us are familiar with, which is dispatch. We defined a group and videos and video URLs. Next, we kicked off an a photo upload operation, and we assigned it to the group. Then we also kicked off a video upload operation, and we assigned to the group again. Fine. We are waiting for the group to finish all this assigned task, and we publish the post. This works really well and leave us with pretty clean-looking code, but we still haven't addressed the lack of error handling here. And we still blindly upload the post, whether or not the media completed or not. To solve this problem, there's another way, introduced recently in Swift 5.5, which is Asynchronous. But before going into that topic, let's see the difference between synchronous and asynchronous method from thread point of view. As a quick reminder, when you call a function that is asynchronous, that is a regular old function, your thread is blocked in this way, waiting for the function to finish. So if you call load user function, your thread can't do anything else. Then after it's done, the thread is free to do the other work now. In contrast, if you call the asynchronous version of that function with completion handler, while it runs, your thread is free to do other work. When it's done, it will notify you by calling this completion handler, like this. First, we spawn the thread, then we call load user. The thread now is free to do other work. When it's done, we just call the completion handler again. To put all this into perspective, let's dig deeper into the implementation of our upload method. The function takes its first argument as data and a completion handler that is used to give the output back to the caller. When upload is called, first the system assigns it to whatever thread to be on. Then we call URL string initializer. This method is synchronous. Then we call URL request with URL. Both of these operations returns value very quickly, so it is fine to run them on whatever thread the function happens to be, and then free the thread quickly. Next, we call upload task on the URL session instance, passing the URL request and the completion handler. It synchronously produces a URL session data task, which must be resumed to kick off the asynchronous work. Upload method then returns, and the thread is free to do other work now. Eventually, either the image finish uploading or something goes wrong. Either way, the request completes, and the completion handler to upload task is invoked with several optional values like data, response, and error. We try to parse this error and data, and if something wrong, we'll notify the user. But there's a problem. Upload method's caller expect to be notified when upload finishes its work, and currently we are leaving the caller in alert. We are so used to writing guard, else, return, and that we forget to invoke the completion handler twice in this method. So if you're creating a URL from a string or decoding response fails, the caller of upload will never be notified. It will just show a spinner forever. To notify our caller, no matter what happens, so every path through the function should notify them. To do that, we need to invoke the completion handler if an error occurs and pass the error along. We saw how it's hard and tricky to get a synchronous operation done right using the formal method. Singleweight, you can write asynchronous code that is just easily as you write regular code, and if you do, your code will better reflect your ideas and intents. So this time we used Synchronous. The function still takes a data as an argument, but while last time a completion handler was passed as well, this time instead the function is asynchronous. When you mark a function asynchronous, the keyword should go just before throws the function signature, like this, or before the throw if the function doesn't throw. Asynchronous will let it wait the result and be suspendable. Next, it starts uploading data by calling upload data task for requests on a shared URL set. Before, this method is provided asynchronous and awaitable. The upload method is awaitable, so after it's called, it suspends itself quickly, unblocking the thread. The thread is then free to do other work. Now we receive the response, the decode method is called, and the upload method returns. So we wanted to perform 3 different operations, one after another in sequence. This is now achievable by switching to Synchronous methods. This is the new shape of our publish post after refactoring from completion handler to Synchronous. And this is our final method, a final publish post method. Here we try to await upload image. Then after we get a result back, we try to await uploading video and finally publish the post. Needed to be performed in sequence are listed one after another. And Swift makes sure that a function always notifies its caller when it's done, either by returning or if a problem comes up. This is just one example of how using Synchronous you can transform your asynchronous Swift code making it safer, shorter, and making it better to reflect your intent. But still, we can do better without sacrificing the code readability. The newly introduced async-let syntax, we can perform a static number of tasks concurrently. By going this way, we speed up the upload time up to 2 times. So now it is time to group tasks together. Now our app supports uploading multiple videos and images. To do this on a model level, all we need to do is just to make the videos and photos properties array of data. Now we want to upload all these photos and videos all together. This mission is simple. Loop through all the photos first, then upload them one by one. Even we tried to add syntax. Remember, it only works with a static number of tasks. The operations are still fully serial, as shown here. Async-let is scoped like a variable binding. This means the child task must complete before the next loop iteration begins. But what if we want this loop kickoff task to upload all the currently? The amount of concurrency is not known statically because it depends on the number of photos in the array. For video, the situation is the same. We follow the same approach. Now we upload our post again. What if we want? But if we to upload all of the and videos concurrently, still we can do better and parallelize is task groups. Task is a form of structured concurrency that is designed to provide dynamic amount of concurrency. You can introduce a task group by calling the following the withdrawn task group function. This function gives us a scope object to create child tasks like that tasks that are allowed to throw errors. Here we define the return type of the. Now, when we loop over the photos, we create a child task in a group by invoking its async method. Once added to the group, child tasks begin executing immediately and in any order. When the group object goes out of the scope, the completion of all tasks within it will be implicitly awaited. So here we are awaiting the URL of every image, then appended to the image URLs array. We do the same to upload video. At this point, we achieved the concurrency that we wanted, but there is still a room for some improvements. What if we want to upload a media, all media attachments all together concurrently? We can do so by introducing a new media type, which is just simple enum with 2 cases, photo and video that has 2 associated types, data and URL, and then we try to extract this data and URL in a computed property to use them later. Then we map all the post attachments to a newly introduced media type. In this way, we try to throw all the photos and videos, then we map them to a media type. Now, instead of returning URL, a task group now returns a media type. Now, we kick off an upload operation, media upload operation. We await it. Then we switch over when the upload operation completes, we switch over the media type and append the photos and URL, photos and video URLs accordingly. Now we really achieved a good level of concurrency. Way, like we have published that upload all the upload operations concurrently, all happen at the same time. So we made a big achievement. There's some cases when you want to bridge both worlds, synchronous and asynchronous worlds. Sometimes we find ourselves in a situation like we want just to wrap a synchronous method into a synchronous call. All that is missing is a bridge to await the completion handler and resume with the fetch request result. So here's the asynchronous version of the upload video method that was written with completion handler. This pattern comes up all the time, and it has a name, a continuation. A continuation provides a powerful way to manually take control over the execution of an asynchronous function. Let's see how continuation can help us writing our asynchronous alternative. The with checked throwing in continuation function lifts completion blocks with error up to throwing a Swift function. The continuation value provides a resume function into which we place the results from the completion handler. And that is all. We are done. We successfully refactored our synchronous method to synchronous version. There are other situations when you want to use a synchronous function in non-asynchronous context. For example, here we have a view.load provided by UIKit, which is non-asynchronous function. And at the same time, we want to use load post with ID, which is synchronous function inside view.load. The Swift compiler is telling us that we cannot call a synchronous function in context that aren't themselves asynchronous. Here, the view.load is a plain non-async method, so there needs to be a way to bridge the gap between the synchronous and the asynchronous worlds. The solution is to wrap the call in asynchronous task. Task gives us access to a new asynchronous context in which we are free to call asynchronous marked APIs and to perform more work in the background. Then we wrap the task. Now let's see its effect from threading point of view. Since if view.load is calling on the main thread, it's a UIKit method, so it's called on a main thread. Task inherits the execution thread from the caller. Since the view.load is called on the main thread, take time. So it will block the main thread, resulting in a bad user experience. Thus, loading should happen at a lower priority. Let's see how. Here we are rendering the UI, for example, calling view.load and view controller views lifecycle. Then we are trying to load, which is a non-trivial task that hit the I/O and go hit network and get result back, which takes time. Then we update the UI. Loading should happen at lower priority. That doesn't interfere with the main UI. For maximum flexibility, Swift provides the attached tasks. Like the attached tasks are independent from the context. So let's kick off the loading by using the attached task. Now, when we detach task, we also get a lot of flexibility in setting up how that new task executes. loading should happen at lower priority. It doesn't interfere with the UI, as we said earlier, and we can specify background priority when we de-attach this new task. So if you notice here, we call the render called on the main thread, while the load post now is called on the background thread. And we update the UI again on the background thread. Let's go back and just to show something. Here in the task, if you notice that we didn't implicitly specify self. The second thing is we didn't use dispatch queues for dispatch queue or dispatch main queue to render the post on the main thread, because task already did that for us, because view controller on the main actor. And here in the de-attached version of that task, if you notice that we now have to use self explicitly here in that version. So let's recap what we have seen today. First, we tried async-let syntax, which allowed us to perform static number of tasks concurrent, or static number of tasks concurrently. Then we saw how task group works, which on the other hand it gives us the ability to perform a dynamic number of tasks concurrently. Then we saw the task, which allow the execution of concurrent asynchronous method from non-asynchronous context, which inherits the execution from the parent, as we saw earlier. Then we have the de-attached version, which allow execution of concurrent asynchronous method from non-asynchronous context. Then finally, we saw how with continuation work, with checked continuation, with checked from continuation, which both used to bridge the gap between non-async and asynchronous methods. So we are at the end of our talk today. Thank you for listening, and if you have any questions, the question section, I will try to answer them. Thank you for watching. Enjoy the rest of the conference.